scattering experiment according to Rutherford clearly shows how the inner structure of atoms and their size can be determined from the angular distribution of scattered small particles. The historic experiment was conducted in 1909 by Ernest Rutherford with the help of his two assistants Hans Geiger and Ernest Marsden. It consisted of an alpha emitter directed at a gold foil. The gold foil was about 0.5 micrometers, only about 1000 atomic layers thick. Radially symmetrical around the gold foil was a fluorescent screen on which the positively charged alpha particles were detected. Before this experiment was carried out, the idea of the atom according to J.J. Thomson was widespread, known as the idea of the Plum pudding model. According to this model, the entire electrically neutral atom is expected to consist of a positively charged mass with embedded electrons. According to this model, the alpha particles would pass straight through the foil, since the entire mass distribution would be homogeneous. The experiment carried out here is modeled on the historical Rutherford experiment. It consists of a cylindrical chamber which is evacuated by a vacuum pump to minimize scattering reactions on remaining air molecules. The chamber consists of a detector for alpha particles, a pivoting americium-241 source, and a pivoting gold foil. Americium-241 decays into excited states of neptunium-237 by emitting an alpha particle with about 5500 keV. The signal from the detector is sent to a counter. First, the gold foil is swung to the side. The alpha source is directed precisely at the detector. A maximum count rate is observed at the counter as the alpha particles easily reach the counter. Now the source is rotated by a small angle around 3 to 5 degrees relative to the detector. The counting rate of the detector drops to 0 because the alpha particles all fly past the counter. In the next step, the gold foil is rotated between the adjusted source and the detector. The counting rate increases slightly. Alpha particles are scattered by 3 to 5 degrees at gold atoms and thus detected. An extensive series of measurements shows that numerous alpha particles are scattered at a small angle, but some are almost completely backscattered at a high angle. In the last part of the experiment, we turn the gold foil aside again, point the particle source back at the detector, turn off the vacuum pump and open the valve. Air flows into the experimental chamber and the counting rate drops rapidly to 0. The alpha particles are scattered to the many air molecules in the chamber and do not reach the detector. Rutherford explained the observation as follows. The observed angular distribution of the positively charged alpha particles corresponds to the repulsor scattering at a single point-like, massive, positively charged object, where theta is the scattering angle with respect to the axis of the incidence. The positive charge of the atoms is thus concentrated in a massive atomic nucleus, while the negatively charged electrons form the almost massless atomic shell, and due to their low mass have virtually no influence on the scattering reaction. Atoms are essentially empty except for the atomic nucleus. By varying the radioactive source, higher energy alpha particles were also used. These can get closer to the atomic nucleus. The higher the energy, the smaller the minimum distance to the nucleus. As soon as deviations in the angular distributions occur, new forces must come into play. The atomic nucleus is almost touched, but Rutherford was even able to estimate the size of atomic nuclei. Atoms are about 10 to the power of minus 10 meters in size, atomic nuclei about 10 to the minus 14 meters in size. The Rutherford experiment is a key experiment in modern physics. By measuring the angular distribution of scattering reactions, it was possible for the first time to study structures and objects that are smaller than the wavelength of visible light, that is, that cannot be seen. Elementary particle physics or electron microscopy is based on this principle.